Hi, my name is Cliff Buxbaum, and this is my final project video for Dr. Mitchell's remote sensing course at University of Maryland. The goal of this project is to design, calibrate, and field test a portable, low-cost remote sensing system that can map stationary targets. Now, you may ask, what is remote sensing? Remote sensing is collecting data about a target without being in direct contact with that target. This is usually done with a sensor that receives acoustic or electromagnetic radiation from the target. Remote sensing systems can be passive or active. Passive systems contain only a receiver and rely on ambient radiation to provide information about the target. Passive systems have limited application, however. Because they rely on ambient radiation, such as sunlight, it can be difficult, if not impossible, to filter out undesired returns from a desired target. Passive systems also tend to have limited range because most natural radiation sources are not very strong. Active systems bypass this problem by providing their own source of radiation. Active systems have a transmitter as well as a receiver, which is usually tuned to only receive radiation from the transmitter. The unique signal from the transmitter can be isolated from other returns, which allows for greater clarity in the final data. Active systems also tend to have greater range than passive systems, because they can provide radiation at a much greater intensity than occurs naturally. This project will focus specifically on LIDAR, which uses visible light as the radiation source. LIDAR systems use a laser as the transmitter and a telescope or camera lens as the receiver. The laser fires a beam of photons at the target. The photons bounce off of the target and return to the receiver, and the data collected from the photons hitting the receiver is processed to create a visual reconstruction of the target. My LIDAR setup will use a far-hop red line laser, shown here in this picture, and here as a close-up, which as the transmitter, and a Raspberry Pi camera, here and here, as the receiver. In order to collect data accurately, I will be using the Bubble Level app on my spare phone to record the angle of my system as I collect data. The data will be collected and stored by the Raspberry Pi, and then sent to my laptop for processing. These components are attached to a 3D printed mount, the design of which was provided by Dr. Mitchell. The mount was too big for the 3D printers on campus to print in one piece, so I printed it in two halves and bolted them together on an aluminum strip. I ran one of the bolts through the aluminum strip and onto the tripod to keep it secure. The benefit of this design was that the aluminum strip added structural security to the system, but threading the bolt through the tripod mount meant that I could not remove my LIDAR from the tripod without loosening the connection between the two halves. I secured each component to the mount based on how permanent I wanted the connection to be. The camera is secured with M2 screws. The laser was initially secured with an M2 screw until I got it aligned, at which point I hot glued it in place. I placed a command Velcro strip, shown here, on the mount and another to the back of my spare phone, and I used zip ties to attach the Raspberry Pi. The laser is powered directly by the Raspberry Pi, and the Pi is powered by a 5.2 amp hour battery pack. I left the battery pack on the ground in part because I was running out of space on my mount, and in larger part because the added weight on the mount made it liable to topple over when on the tripod. This system uses geometry and known distances to calculate the range to the target. My laser and camera are fixed at 12 inches apart, and the camera has an angular field of view. The camera also has a set number of pixels regardless of range, which means that the pixel position can be related to position within the camera's field of view. The angle between the object's return and the camera's central axis can be calculated with the measured pixel position on the return, and this angle can be used to calculate the known distance between the laser and the camera to calculate range. In order for my LIDAR system to accurately collect data, it needs to be calibrated. I did so by collecting data from a wall in my apartment at 6-inch intervals from 2 feet to 10 feet. In video of my calibration images, you can see that the laser return gets closer to the central axis as the wall gets farther away from my LIDAR. On the left is the calibration curve for the correction values I used. Since the fit was just about perfect, I moved on to testing the system in my apartment. The target in my apartment was a couch. I scanned the couch from bottom to top in increments of 1 to 3 degrees. On the left are images that my Pi sees, and on the right is a masked version of each image where you can see the laser returns in white. After I collected the data, it was time to process it. I used a Python code provided by Dr. Mitchell with a few edits to make sure the data was calibrated to my LIDAR. I want to quickly run through a few important sections of the code. On the top left is the code for the HSV mask that will be applied to each of the images. The provided inputs are the HSV code for red light. On the bottom left are the parameters for calibration used in the geometric calculation that determines the range for each return. They include the radian offset, the radian to pixel conversion, the separation distance between the transmitter and the receiver, and the angle for the camera's field of view. On the right is where the magic really happens. It's an if-else statement that calculates the range, then takes that range along with the angle of the LIDAR to calculate the position of the return in Cartesian coordinates, and finally output those coordinates to a text file. The else statement here sets any non-returns, meaning any returns within the masked image that aren't white, to 0. After creating the text file for the point cloud, I used PCShow to plot that cloud in Matlab. The cloud came out pretty well. You can clearly make out the base, back, and one of the arms in the resulting cloud. With everything set up and tested, it was time to take it outside and test it on my target object. The target is a small defunct fan just outside Martin Hall by the lower entrance to the cafe. I chose the object because it was well suited for mapping. It's not too big to get a good resolution, it has a fair amount of flat ground around it, and it doesn't have too many lights around it. It also has a lot of interesting features. Some features I really wanted to capture were the power box, the fan itself, and this rounded back here. In order to get as much coverage as possible, I took 5 scans of the fan, 1 from head-on, 1 from each side, and 2 from angled views. I could not get any scans of the back because the fan is up against the wall. Once I collected my images, I ran them through the Python code. With my clouds for each scan saved as text files, I plotted each cloud in Matlab to confirm that they came out okay, and then loaded the clouds into Cloudcompare. I used the segment function to crop out any stray points from the noise and other structures that came up in my scan. After cropping out unwanted points, I added other scans and manually aligned them using the Translate tool. I rotated new scans 1 axis at a time until they were aligned, and translated them until they fit. Overall, I think my cloud came out pretty well. Each of the features that I was looking for was visible in the point cloud. The fan is clearly defined, and while it's hard to see in the final cloud, I even got some returns from inside the fan. The hole in the bottom came out clearly, as did the power box. I even got some pretty good clarity on the rounded back of the fan. The one thing I'm not pleased with is the fact that my clouds came out just a bit crooked, and each of them inconsistently. So, I think the main reason for this is due to minor errors in my angle recording. After I finished my cloud, I used a Poisson surface reconstruction to create a mesh of my point cloud. I then ran a Laplacian smooth function to clean up the mesh and make it a little prettier. The mesh did not come out quite as well as I had hoped. You can still make out some of the key features like the power box, the hole near the bottom, the fan, and the back, but they're not nearly as clear as the cloud. Now I want to talk about some of my challenges. The first challenge I dealt with was a glitch when setting up OpenCV. For some reason, the environment didn't want to make itself, but this resolved itself after just restarting it about half a dozen times. My next challenge came when trying to assemble my LIDAR. I initially tried to connect the two pieces of the mount with glue, but that failed, and after that I decided to go with the aluminum. Going past that, I had some errors with calibration. I couldn't get a HSV mask that worked properly, and I finally realized that the main issue was that I was collecting data, or I was using data that didn't have any laser return on because it was too close to the pi. Once I cut those images out and ran the calibration again, I was able to get a perfect setup. My next issue when running the apartment scan was I found that the laser didn't show up on the camera. I found that the main issue for this was due to a lack of exposure on the camera. When I changed the code to allow the camera to give the camera much greater exposure, the laser showed up clearly, as seen in the various images. Once I was done with that, I had to wait a couple of days before I could actually take data, as it rained the next 2 nights, and you can't bring sensitive electronics outside in the rain. After all that was done, I had to download and learn about half a dozen new programs, including OBS, Cloudcompare, Adobe Premiere CC, and using editing in photos. But fortunately I made it out.